Okay, so here are some of the announcement that I want to share muna, no? Okay, so the first announcement will be this one. Okay, so on your Canvas announcements dito, I posted something there, no? So may pinost ako doon that's additional reference material. So in this post, I upload no the worksheets that we use no in the lecture and in the laboratory, which can help you when you're reviewing for the quiz and the midterm exam now. Okay, so for the lecture, since you're about to take quiz 3, parts 1 and parts 2, I already uploaded some of the questions with answers here now. So the purpose of this post no, is to help you with your review. So hopefully this helps. No? So ito yung tsura nila. No? So this is how it looks like. So for the part 1, the topics are the following: writing equilibrium constant, operations with equilibrium constant, so on and so forth. Okay. So I have sets of question here. So I want you to answer that first, and then once you're done, you can check your answers on the proceeding pages. Okay. So that is how it looks like. So same thing as for part 2. So for part 2, there are some questions here on the front, okay, and then the solution will be posted on the preceding pages, okay, complete solution, okay. So hopefully this will help you when you're taking the assessment, okay. Other than the lecture, I also posted here some laboratory worksheets, no? So just in case you want some more examples in the laboratory, I also posted them here. So we have 3 worksheets already in the laboratory because all of those contains calculation. Okay, so for chapter 1, I have posted this thing here, solutions answer key. So if you want to review your solutions, you can check this out. Okay. For statistics, I also uploaded a file, okay, about statistics. Okay, so and then the latest one is the gravimetry. Okay, so I hope you were done with gravimetry by this time in your laboratory class now. Let me just view this. Okay, ayan. Okay, so yeah, so hopefully this will help you when you review for your quizzes and later on the midterm exam. I will upload more materials before the midterm exam. So hopefully around a week before the midterm exam, I can upload some more examples that will help you with your review. Okay, so please maximize the use of these materials. Huh? Okay, so I want you to really work on this because as you can see, analytical chemistry is quite hard talaga, no? Especially with calculation part. Okay, so this is the first announcement. The second announcement would be on the quiz. Okay, so again, quiz 3 has 2 parts, parts 1 and parts 2. For part 1, for part 1, the coverage is about the topics we discussed last week. So that's about writing equilibrium constant, Kc and Kp, basic equilibrium calculations, and then predicting the direction of reaction using Q and K. Okay, so those are the only topics covered in this part. So that's 20 points. The passing score would be 10. You will be given 60 minutes to accomplish this quiz. Only one attempt will be given as well. Okay, so this will be open starting Feb 26 until March 1. Okay. By the way, if you want for Filipino students dito, if you want Taglish version of my classes, you can check out the videos of sections 1 and 14. Okay, so yun. So if you want Taglish videos, you may want to check out the content for these two sections here. Okay, and for part two, this is the coverage equilibrium using ice table and the Chatier principle. Okay, this is the thing that we're going to discuss today. Okay, so 20 points and 45 minutes for each attempt. You will be given with two attempts, and the highest score will be recorded. Okay, so this will be available starting March 3 until March 6. Okay, so good luck. So for now, just review for this part, huh? Just review for the part one, and over the weekend, review for part two. Okay. So use the worksheets I uploaded to help you with your review. Okay. Okay. So anyway, that's all. The third announcement will be about this video. So yesterday, I think that's yesterday. I already uploaded a video about solving for x using calculator. This technique is helpful, especially for this topic, since we will be dealing later on with quadratic equations. Okay, so in dealing with quadratic equation, you can solve it manually using the quadratic formula, or you can make use of your calculator. So our calculator are sometimes capable of solving for complex equations. No. So you may want to check this video. I already posted the link on our chat box. Okay. So that will help you on how to solve for the values of x when dealing with quadratic equations or trinomials, no, etc. Okay. So hopefully this will also help. Okay. So that's all for the announcement. Okay, so now let's proceed with our main topic. So our main topic today is about the equilibrium calculations in with the use of ice table and the Le Chatelier principle. Okay, so last time we were able to discuss the equilibrium constant. We said that equilibrium is a state of a system, or that is a state of a solution in which the rates of forward and reverse reactions are equal. So that means some of the reactants are being converted to products, and also at the same time, your products are being converted back to reactants. So those two instances happen at the same time. No? So whenever we have such case or such state for the system, then we have a chemical equilibrium. So two reactions are happening at the same time, the forward and the reverse reactions. In writing the equilibrium constant, okay, so an equilibrium constant is a mathematical tool that describes the equilibrium system. So in writing the equilibrium constant, that is just the concentration of products over reactants, wherein your coefficients will serve as the exponent for the concentration of your substances. Okay, so for this particular example, capital letters A, B, C, and D are our substances, and their small letter counterparts are these coefficients, okay, of a stoichiometric equation. Okay. So anyway, so for substances C and D, they have to be multiplied in the equilibrium constant, same as for substances A and B. And also take note that the coefficients will be the exponent for the equilibrium constant. Okay. Um, yan. Okay. So in writing the equilibrium constant, we have two ways of writing them. We can either use the Kp or the Kc. So when we say Kc, this pertains to the equilibrium constant wherein the concentration of your species are expressed in molar units. Okay, so that's mole per liters. The Kp on the other hand, is an equilibrium constant in which your concentration of the species are expressed in terms of atmospheres. No? For aqueous system, we only have the Kc, okay, and for gaseous phases, we both have Kc and Kp, okay, because we can express the amounts of gases in terms of pressure and molarity as well. Okay, and then also last time we related Kc and Kp. Okay, so if Kc is given, you can solve for Kp, or if Kp is given, you can solve for Kc. Okay, so to solve for those species, you just have to use this equation. Okay, so that's Kp equals Kc parenthesis RT raised to delta N gas, wherein delta N gas is the difference of moles of your gaseous products and the gaseous reactants. Okay, so we're going to subtract how many moles of gases in the product you have and the number of moles of gas you have in the reactant. Okay, what else? Last time we were able to cover the operations with equilibrium constant. So as I told you last time, the value of equilibrium constant depends on how you write the equation. Suppose in this part, if you reverse the equation, that means the equilibrium constant becomes the reciprocal. Okay. For this one, if you divide the equation by 2, then the new equilibrium constant is equal to the square root of the original. Na? If you multiply the coefficients by 2, then the new equilibrium constant value will be square of the original. Okay? So depending on how you balance the equation, there is a corresponding k value. Divide the equation by 2, you will get the square root of your k. You multiply the equation by 2, you get the square of your k. If you multiply the equation by 3, you get the cube of your k, okay? And then when you divide your equation by 3, then you get the cube root of your k, okay? So depending on how you balance the equation, there's a corresponding k value. And then lastly, when combining equations, we multiply both equilibrium constants, okay? So So this is the summary of the operations I discussed last time, and then also we covered the topic on how to predict the direction of the reaction. Okay, so suppose you are given certain amounts of substances, you may want to check whether the reaction is going to the product side or to the reactant side, because there are two reactions happening at once. So in order for them to establish equilibrium, the system must proceed in just one direction, no, in order to achieve the equilibrium or to achieve the balance. So for us to predict where the reaction is going, so we have to compare K and Q. Okay, so K is the value, or this is the equilibrium constant at equilibrium. Okay, so how, however, for Q, this is the reaction quotient. So it tells you the ratio of the products and the reactants initially, okay, before the reaction becomes an equilibrium state. Okay, so depending on the value of K and QC, you can tell whether it is going to the left, going to the right, or it is already on the equilibrium state. So if Q is less than the K, so again, blue circles are the K values. So if your Q is less than the K, then that means there are more reactants than products. So you have to move your reaction to the right. Okay, so the reaction will proceed towards the right to achieve equilibrium. If your Q is already equal to K, then there's nothing more to do. It is already in equilibrium state. Okay. However, if your Q is less, if your Q is greater than K, okay, so this is Q, this is K, so that means there are more products than your reactants. So that means in order to achieve balance, some of the reactants will be converted to reactants. Some of the products will be converted to reactants. So that means the system will shift the equilibrium to the left. Okay, so that means the reaction will proceed towards the reactant. Okay, So again, depending on the value of Q, you can either have a reaction going to product, going to reactant, or it is already balanced. Okay. So you just compare the values of Q and K. So this will be useful with our main topic today. Okay, so those are the things we discussed last time. So now let's proceed with our main topic, equilibrium calculations. Okay, so yeah, so let's get started. So the problems that we're going to encounter here gives us the initial amount of our chemical species, and then we will be asked later on to solve for the equilibrium concentration. Okay, so again, we will be given the initial concentration of our chemical species, but the problem will ask you the equilibrium concentrations. Okay, how is this different with our previously answered questions? Okay, so for the previous questions we answered, we are actually given the equilibrium amounts already. Okay, so we are given the equilibrium amounts here on the previous questions we had last time. Okay, however, in our case today, we will be given the initial concentration and we will solve for the equilibrium concentration. Okay, the question is that possible? The answer is yes. Okay, so from our initial amounts of the substance, we can determine the equilibrium concentrations by using the equilibrium concept and the predicting of the direction of the reaction topic. Okay, so we can address this issue by identifying where the reaction will go, and then later on we can solve the question using equilibrium constants. Okay, okay, so again, the questions in this topic will give you the initial amounts, and then later on it will ask you for the equilibrium concentration. Okay, so how are we going to address this question? Okay, so how are we going to solve this? There are three easy steps. Okay, so number one, uh, you want to create the ice table first. No? So I forgot that step. Okay, so you're going to create the ice table. Some references call it the rice table. Okay, rice table. So what is the ice or the rice table? So the ice and the rice table will allow us to see, or will allow us to track the changes in the concentration of our chemical species as it achieves equilibrium. Okay, so this is a table where we can see what's going on with the equilibrium system. Is the products increasing or is the reactants increasing? Okay, so we can see that with our ice table. Okay, so what is I in the ice table? So I is the initial amounts. Okay, so you have to write whatever is told to you in the quiz, in the question. So you're going to input there the initial amounts given already. That's the I, initial amounts. That's all given. For the C, this is the changes in the equilibrium. Okay. So recall that we can actually predict the direction of the reaction. So that means the changes could either be positive or negative. No? Suppose the reaction is going to the products, then the change for reactant is negative because the amounts of reactants will decrease as some of it will be converted to product. Okay. Okay, so that means if the reaction is going to the product, your reactants change will be negative because their amounts will decrease, and your product change will be positive, no? Because the amounts of product will increase over time, okay, in order to achieve equilibrium or in order to achieve balance in terms of concentrations. Okay. If your reaction is going to the reactant, that means your product change will be negative, okay, because the products will be decreased over time because some of it will be converted back to the reactant, okay. So that means the change for the product will be negative and the change for the reactant will be positive, okay. So depending on the direction of the reaction, your change could either be positive or negative for the reactant and the product side. Okay, so that's the I for the ice table. It will tell us the change. Okay. Question here is that do we already know how much change will happen? Okay, so do we know how much change will happen to the reactant side or to the product side? We don't know yet. So that's why we have to use a dummy value. That's why we have to use a dummy variable x. So x is a single unknown quantity which will tell us by how much the concentrations of your reactants and products change. Okay, so we're going to write down plus x minus x, okay, in the ice table. And for E, that's the equilibrium concentration. Okay, so for E, that is the sum of your initial and the initial concentration and the change in concentration. So you're just going to add the two terms that will give you the E. And then whatever is written in the E, that is equivalent to the equilibrium constant. So as you plug in the expressions for E in the equilibrium constant, you can now solve for the value of x. Okay. Then once x is determined, you calculate for the equilibrium concentration of the other species. Okay. So let's have some examples so that we will clearly see these problems. We will see clearly how to answer this question. This type of questions here. Okay, so let's have number one. So isomers of steel bean have an equilibrium constant of 24 at 200 degrees Celsius. The equation is given below. Suppose initially there is 0.85 molar cis isomer. Calculate the equilibrium concentration of all species. Okay, so again, the format of our equation here, the format of our questions here is this. It will give you the initial amounts of your species, and then it will ask for the equilibrium concentration. So whenever you see problems like this, initial amount is given, you're asked for the equilibrium concentration, then that means you have to use the ice table. Okay, so you have to use the ice table in order to answer this question. Okay. Wait lang. Di ko mabura yung nakalagay. Wait lang. I'm having problems with my PowerPoint. I cannot delete my writings. Let me just reopen this. Okay. Okay, so going back again for this question here, ito. Okay, so again, the format of the question here is that it will give us the initial amounts and it will ask for the equilibrium concentration. If that's the case, then we have to use the ice table. Okay, so let's construct first the ice table or the rice table. So we have the reaction here on front. So we have the cis isomer converting into trans isomer. Okay, so let's write the I, C, and the E. Okay, so the I, C, and E. Okay, so since this is table, you may want to uh, show the table part. No? You want to draw lines. Okay. Okay, so this is the ice table or the rice table. So the R represents the equation. Okay, so rice table or ice table. So what you're going to do here is that you're going to plug in whatever is given in the problem in the question in the table. Okay, so our question states that there is 0.85 molar cis isomer, 0.850 molar cis isomer, and then we're going to solve for the equilibrium concentration. Okay, so nothing else was given, just the initial amount of the cis isomer. So that means initially we have 0.85 molar cis isomer and we have how much trans isomer. So because the question didn't even mention the trans isomer, that means we do not have any trans isomer. Okay, so we don't have trans isomer. Okay, so that's the info that we're going to write down on the I part. Okay, so in the initial part. Okay, so cis isomer is 0.85 molar. For the trans, that's 0 because it wasn't mentioned in the problem. The amount is not mentioned on the problem. Okay, so that's the I. Okay, so cis is 0.85, trans is 0. How about C, change? Okay, so as I told you last time, the change for our species could be positive or negative for the reactant or the product side. Okay, depending on how the reaction is proceeding, or where the reaction is going. Okay, so for this particular case, you may want to check the for the value of Q and the K. No? So you're going to compare Q and K. So you can tell which one is positive. Is that the reactant or the product side? Okay. So let's compare Q with the K. Okay. So for Q, the equation is product over reactant. Okay, initially. Okay, so their initial concentrations. Okay. So according to ICE table, the concentration of our product is 0. And the concentration of our reactant is 0.85. Okay, so what's 0 divided by 0.85? That is 0. Okay, so that means our Q is 0. However, the value of K is 24. Okay, so if we compare Q and K, okay, we draw a number line. So in the middle, we have the K equals 24. That means Q is on the left. Okay, Q is equal to 0. That's on the left. Okay, so in order to achieve equilibrium, that means your reaction must proceed to the right side. Okay, so our reaction must proceed to the right side, to the product side, in order to achieve the equilibrium. So how are we going to translate that info on our ice table? Okay, since the reaction is going to the right side, then that means the change for the product side is positive x. Okay, so why positive x? Because this this part, okay, I mean, teka lang. Okay, so this part of our solution here, this tells us that the reaction is going to the product side. That means the change for the product side must be positive because over time it will increase. Okay, their concentrations will increase on the product side. Okay, so for the reactant side, no, since some of the reactants will be converted to products, then the change for the reactant must be negative. Okay, so again, if your Q is less than the K, that means the reaction is going to the product side. Hence, the change for reactant is negative, and the change for the product will be positive. Okay, so negative X for the reactant because over time, its amount will decrease as some of the reactants are being converted to products in order to achieve equilibrium. Okay, suppose you have coefficients here. Suppose you have two coefficient here. You have number 2 here. So the change will be negative 2x. Okay. So whenever you have coefficients, you have to introduce it to your change. Okay. So if suppose your coefficient here is 3, then your change will be negative 3x. Okay. Because this question will still follow the law of conservation of mass. Okay. Right, so suppose you have a coefficient 4, that means your change will have a coefficient of 4 as well. Okay, so we follow the conservation of mass. So whatever the coefficients is, you have to type it into the change row. Okay, you have to plug it in on the change row. Okay, so that will be the I. So again, I, or the initial concentration, that's already given in your problem. Okay, so if the problem doesn't mention that chemical species, then that means it is 0. Okay, For the change, you may want to compare Q and K. Okay, so if your Q is less than the K, then that means for the reactant that's negative, for the products that's positive. What if your Q is greater than K? Okay, so if your Q is greater than K, then your product will be negative, then your reactant will be positive in terms of change. Okay. How about E? So for E, we have the equilibrium here. So what you're going to do is to add I and the C. Okay, so yeah, you're going to add I and C. Okay, so that will be 0.85 minus X for the cis. That will be the concentration of cis at equilibrium, 0.85 minus X. And then for the trans, that is 0 plus X, which is just 0. Okay. So at equilibrium, the concentration of cis is 0.85 minus X. And the concentration of trans is X. Okay. So again, how were we able to solve for this? You just add I and the C. Okay. Add this plus this. That will give you this part. And this plus this will give you X. Okay. So once you have the equilibrium expressions with unknown variables in it, so you're going to plug it into the equilibrium constant. Okay, so let me just erase this part here on the right side. I still can't use my pen tool. Okay, so anyway, so I have to rewrite everything. Okay, my PowerPoint is acting up. Okay, so again, cis trans ICE. So cis is 0.85, trans is 0. So that means the change for the reactant is negative, and for the product side that is positive. Okay. So at equilibrium, the concentration of cis is 0.85 minus X. For the trans, that is just X. Okay. So again, we're going to plug in the equilibrium concentrations in the equilibrium constant. Okay. So let me write down the equilibrium constant. So the equilibrium constant is the concentration of trans isomer over the cis isomer. Okay, so that's the equilibrium constant for this equation here. That's trans over cis. Okay, and then next you're going to plug in the equilibrium concentration for cis and the trans. You're going to plug in this here and this one here as well. And then the value of k is already given. We're also going to plug it in the equation. Okay, so we're going to plug in whatever is said in our solution here. Okay, so for k, that's equal to 24. For the concentration of trans, that is just x. Okay, and the concentration of cis, we have 0.85 minus x, so 0.85 minus x. So what's next is that you're going to solve for the value of x. Okay, so once you were able to plug in the equilibrium concentrations and the k value, you're going to solve for the value of x using algebra. Okay, so the chemistry stops right here, and then algebra will kick in. Okay, so let's solve this algebraically to find the value of x. Okay, so using algebra, we're going to solve for x. So what are the steps? So you may want first to cross multiply this into that. Okay, so you're going to cross multiply your denominator here to the numerator there. Okay, so let's cross multiply them so we can solve for the value of x. So that will be 24 times 0.85 minus x. Okay, so after cross multiplying them, next thing is that you're going to distribute 24 to our binomial here. Okay, so we're going to distribute 24 to our binomial. Okay, so that will be x equals 24 times 0.85. Use your calculator to solve for that. 24 times 0.85 is 20.4. And then 24 times negative x is negative 24x. What's next is that you combine similar terms. Okay, so you're going to combine all the x's and all the numerical coefficients only. Okay, so we have 24x here on the right side. You want to combine it with the x on the other side. Okay, so we're going to add 24 on both sides so that 24x will be cancelled on the left side, on the right side rather. So let's add 24x on both sides so that uh, our x will be on the same side. Okay, so it's 24x plus x, that will be 25x. That's equal to 20.4. Okay, and then we're going to solve for the value of x. So the value of x is equals to 20.4 divided by 25. Okay, so what's 20.4 divided by 25? That is 0.816. Okay, so that means the value of x in our ice table is 0.816. Okay, so that's it. Okay, so once you were able to solve for the value of x, you are going to plug it into your ice table. Okay, so that means the equilibrium concentration of cis will be 0.85 minus 0.816, and that will be equal to 0.034 molar. And for the trans isomer, that is just 0.816 molar. Okay, so that means at equilibrium, the concentration of the trans isomer will be 0.816 molar. The concentration of your cis isomer will be 0.034 molar. Okay, so that's how we solve for this type of question. Again, let's recall, we are given the initial amounts, we are asked to solve for the equilibrium concentration. So for you to solve for the equilibrium concentration, you have to use the ice table. On the ice table, you're going to type in whatever the information was said in your problem. Okay, so for the I, that is the initial concentration. Okay, so in this problem, we have 0.85 of the cis, 0 for the trans. Okay, because it doesn't mention the trans isomer. Okay, so we have 0.85 for the cis, for the trans, that's 0 because it was not mentioned. Okay, for the C change, you're going to compare the Q and the K. Okay, so the concentration for the Q can be obtained from the first row, okay, from the I row, okay. And then once you were able to solve for the value of Q, compare it with K, and then from that, you can tell whether the reactant is positive or negative, okay. So in our particular case, Q is less than K, okay. So that means the reaction will proceed towards the product side. So that means the change for reactant must be negative and the change for the product must be positive since our reaction is going to the product side. Okay. What if our reaction is going to the reactant side? Now, what is the change? No, what is the change if our reaction is going to the reactant side? So that will be positive for the reactant and negative for the product. Okay. So again, if your reaction is going to the right side, then that means negative for the negative change for the reactant and positive change for the product. Okay. If your reaction is going to the reactant, then the change for the reactant must be positive and the change for reactant must be negative. Okay. So yeah. Also, if you have coefficients here, you include it in your change. Okay. Change expression. So suppose we have two coefficient forces, then that means the change will be negative 2x. If your trans has a coefficient 3, then that means the change must be positive 3x because we still follow the law of conservation of mass here. So for the equilibrium, what you're going to do is you just add I and C. So add this with this, you get 0.85 minus X. Add this and that, you get X. Whatever your E here, you're going to plug it into the K. Okay, so our X is the trans concentration at equilibrium. So we write it down there. At equilibrium, cis concentration is 0.85 minus X. And the equilibrium constant is 24. Then once everything is plugged into the equation, we can now solve for the value of X algebraically. So on this part, we solve for the value of X, that's 0.816. Then after solving for the value of X, you are going to plug it on the E. Okay, so you're going to plug your X into the E. Okay, so to solve for the equilibrium concentration of all species. Okay, so that means at equilibrium, cis is 0.34, trans is 0.816 molar. Okay, so that's how we solve for uh, this type of problems. Okay, so you're going to use the ice table, and then later on you will do algebra. Okay, to solve for the value of X. Then after solving for the value of X, you plug it into the E to answer the question. Okay, so that will be our first example. So let's proceed with the second example. So on this problem, we have a mixture of 0.75 mole hydrogen gas and 0.75 mole iodine was placed in a 1 liter stainless steel flask at 430 degrees Celsius. The equilibrium constant for the reaction is 54.3 at this temperature. Calculate the concentrations of hydrogen, iodine, and hydroiodic acid at equilibrium. Okay, so again, this problem gave us the initial concentrations and it asks us about the equilibrium concentration. So if you are asked for the equilibrium concentration given the initial amounts, you have to use the ice table. Okay, so let's construct the ice table for this problem. So first you want to write down your uh, you want to write down your problem, your reaction first. No? Okay, so write down your reaction and then construct the ice table. Okay, so construct your ice table. There you go. So what will be the initial concentration of iodine? Hydrogen gas first. Okay, so the initial concentration of hydrogen gas is not stated. Okay, so it was not stated on the problem. However, we have the moles of hydrogen gas and the volume of the volume of the container. So dividing the moles by the volume, we will get the molarity. Okay. So you are not going to plug in the moles on the ice table, huh? You will never plug your moles on the ice table. Only the molarity or the pressure. Okay. So if you have moles, you have to divide it first with the volume of your container. Okay, so you're not going to add plug in the mole as is. No, you have to divide it to uh, the volume, so you will get the molar concentration. Okay, so again, the allowed values for the I is the molar concentration or the pressure only. Okay, so molar concentration and the pressure only. Okay, so that means moles are not allowed. Okay, so you have to divide this by 1 liter. So 0.75 moles divided by 1 liter is 0.75 molar. So that will be the concentration of your hydrogen gas initially. For iodine gas, that is also 0.75 moles divided by 1 liter. That will give us 0.75 molar. For HI, we do not have any figures for that. So that means it is 0. Okay. So if your problem didn't state the species, then it is 0 on the ice table. Okay. So that's the I, okay? So we have 0.75 molar for hydrogen gas, 0.75 molar for iodine, and 0 molar for HI. How about the change, okay? So you may want to compare the QC and the KC, okay, so comparing Q and the K, you can predict where the reaction is going, okay? So I will tell you a shortcut now. So the shortcut is that wherever, um, excuse me. Okay, so the shortcut is this now. If you have zero amounts on the product side, then that means the reaction is going on the product side, okay? Because if you solve for the reaction quotient with species on the product side equal to zero, then that's Q equals zero. Okay, so that means the reaction will go to the product side talaga. Okay, so again, whenever you have zero concentration on the product, then that means the reaction is going to the product side. Okay. Also, if you have zero concentration on the reactant side, then that means the reaction is going to the reactant side. Okay. So where the zero is, the reaction is going there. Okay. So on our problem here, the zero is on the right side, then the reaction must proceed to the right side. Okay. So that will be the shortcut now. You just want to look for the zero first, then where the zero is, the reaction is going there. Okay. So on the right side, we have zero concentration. So that means the reaction is going to the right side. Okay. So that means the change for the reactant side is negative. Okay. So that's negative X for H2, negative X for iodine, and for HI, that will be positive 2x. Okay. So again, HI is our product. The reaction is going to the product. So that means the change must be positive for HI. Okay. Also, take note that whatever the coefficient is, you have to include it on the change expression. So we have a coefficient 2 here. So that means the change will be 2x, okay? So if you have a coefficient 3 here, then that means it will be 3x, so on and so forth, okay? So whatever the coefficient is, you have to include it in your change expression, okay? So let's solve for the equilibrium concentration. So that will be 0.75 minus x for H2. That will also be 0.75 minus x for I2. And for HI, that will be just 2x. Okay. So again, you just combine I and the C to get the E expression. Okay. So let me rewrite this slide. Okay. Let me rewrite this. So our solution will be clear. Okay. So again, for the I, that's 0.75 molar for H2, 0.75 molar for the I2, and 0 for the HI. So since we do not have any products, the reaction will proceed towards the product. So that means reactants will be uh, decreased over time. So that means the change is negative X for them. And for the product, it will increase over time. So the change is positive 2X. Okay. The reason why we have 2 here is that we have coefficient of 2 kasi. Okay. So whatever the coefficient, that must be plugged into the change expression. Then for the equilibrium, we're just going to add I and the C. That will be 0.75 minus x, 0.75 minus x, and then 0 plus 2x is just 2x. So what's next is that you're going to plug in your equilibrium expressions into the equilibrium constant K. So let's write down the K first. So for this equation here, K is written as the concentration of HI squared, okay? And we divide it by the concentration of H2 and concentration of I2, okay? So this is the equilibrium expression for this equation here. What's next is that you plug in your equilibrium expressions and the K value. So K value is 54.3. So let me write it there, 54.3. That's equal to, what's the concentration of HI at equilibrium? So according to the ice table, the concentration of HI at equilibrium is 2x. So we're going to plug in 2x into this, okay? So that will be 2x, then squared, okay? So there you go. Okay, so your 2x will be plugged in here, and it is also squared. Okay, for the denominator, we have 0.75 minus x for H2, and for I2, that will also be 0.75 minus x. Okay, so after plugging in your equilibrium expressions and your equilibrium constant, you can now start solving for the value of x. Okay, so yeah, so let's solve for the value of x. So on the denominator, since you have a product of of two binomials, then you have to do the FOIL method. Okay, so FOIL method, first terms, multiply them, and then the outer term, the inner term, and the last term. Okay, so let's do that now to expand the expression. So on the numerator, we have 2x squared. Okay, so that will be 4x squared. Okay, so 2 will be raised to 2, x will be raised to 2. Okay, so that is 4x squared. Okay, for the denominator, we're going to do the FOIL method. So first term, multiply them. It's 0.75 times 0.75. That is 0.5625. Okay, so that's the product of our first terms, outer terms, inner terms. Okay, so you multiply this with this. That will be 0.75 minus 0.75x. Okay, the inner terms will be also the same. And then lastly, the outer terms, the last terms rather, okay, will be negative x times negative x. That will be positive x squared. Okay, so you do FOIL method, okay, when you encounter this type of question here. Okay, so do the FOIL method, you have this. Okay, you simplify the equation. So 54.3 equals 4x squared divided by 0.5625. You have 0.75 minus that. So negative 0.75 minus 0.75. That will be negative 1.5x plus x squared. What's next? You're going to cross multiply the denominator to the right side. Okay, so cross multiply this to the right side. And so let me write it here. So I'll write 4x squared here. Okay, so you cross multiply this denominator on to this one. Okay, so we will get 54.3 times 0.5625 minus 1.5x plus x squared. Biglang nag-algebra tayo na. Anyway, so yan. So after cross multiplication, what you're going to do is to distribute this to the terms in your parentheses. Okay, so you distribute this into your individual terms. Okay, so if we have 4x squared equals, what's 54.3 times 0.5625? Okay, 0.5625. That's equal to 54.3, 0.56. Okay, so that is equal to 30.54375, 375 minus 54.3 times this term times that term, it will be negative 81.45 x. And then lastly, we have 54.3 times this term plus 54.3 x squared. Okay. What's next? You combine the similar terms. Okay. However, if you have quadratic equation, that means the x is raised to 2, then you have to format your equation into this. No, you have to format it as ax squared plus bx plus c equal 0. So that means we will transpose 4x to the right side. Okay, so that this will this will all be equal to 0. Okay, so let's transpose 4x on the other side. So we get 50.4 x squared minus 4x minus 81.45x plus 30.54375. Okay. So this is 54 pala. So what's 54.4 minus 4x? That will be 50.4 x squared. X squared pala siya, sorry. So what's 50.4? 54.4 x squared minus 4x. That will be 50.4 x squared. So we have 50.4 x squared minus 81.45x plus 30.54375. Okay. So the next question is, how am I going to solve for the value of x? Okay. So in order to solve for the value of x, you have to use the quadratic equation. Okay. So the quadratic equation is negative b plus minus the square root of b squared minus 4ac over 2a. Okay. So what is the value of a? Okay, so the value of a will be the coefficient of x squared. That will be a is equal to 50.4. Okay, so the value of a on our quadratic equation is the coefficient of x squared. So that's 50.4. How about the value of b? The value of b will be the coefficient of x. Okay, so that's negative 81.45. And the value of c will just be the the number lang without x. Okay, so we have this one here on the last part. So c will be the coefficient without any variables. Okay, so that is equal to 30.54375. Okay, so what you're going to do is you plug in a, b, and c into your quadratic equation, and then you can get two x values. Okay, so I'm not going to show you how I will plug A, B, and C, because we already did that in our high school algebra. Okay, so since we know that A, B, and C are equal to these numbers, you just type it into this equation, type it in your calculator, and then we will get two x values. Okay, so according to algebra, the exponent of your x is equal to the number of roots. No? So since we have x squared, we have the 2 as the highest exponent for our equation, then that means we have two roots. Okay, so that means we will get two x values here. Okay, so using quadratic equation, let me just type in the numbers in my calculator, and that will be 50.4. Okay, so using quadratic equation, the two x values are the following. Okay, so x1 will be 1.02425. So that's the first x value if you use quadratic equation. And the second x value will be 0.591. Okay, so again, So again, you solve for the x value using quadratic equation. You can use your calculator when solving for the values of x now. I already uploaded the video on how to do that. Just check the chat box here. Okay. So yeah. So after solving for the value of x, we are going to plug it into our E. Okay. So we're going to plug the equilibrium concentrations in our E. The problem is that we have two x values. Which of the two are we going to use? Okay, so we have 1025 and 0.591. Okay, among those two, only one must be used. Okay, so let's check if we're going to use 1025 or 0.591. Okay, how? Okay, so these are the criteria for the x value. Number one, it must be positive. Okay. Sometimes we will get negative roots from our quadratic equation. So when you get negative x value, discard it. Use the positive value. Okay. However, in our case, we have two positive values. So among those two, only one must be used. So the second criteria for choosing the correct value of x is that x must never, x must, ano, x must not exceed your initial concentration. Okay, so the value of x must always be less than the initial concentration. Okay, our initial concentration is 0.75. So that means we will choose an x value less than 0.75. Okay, because if we deduct 0.75 with 1.025, we will get negative concentration for H2 at equilibrium. Does that make sense? No, because there are no negative concentrations. Okay, so that's why we choose the x value that is always less than the initial concentration. Okay, so again, what are the two criteria in choosing for the correct value of x? Number one, your x value must always be positive. If you have negative x value after solving for the quadratic equation, discard it. Okay, just use the positive x value. If you have two or more x values that are positive, the second criteria will be followed. Your x value must always be less than your initial concentration. Okay, it must always be less than your initial concentration. Because if it is greater than your initial concentration, then you will get negative equilibrium concentrations, and that doesn't make sense. Okay, we do not have negative concentrations at all. Okay, so between 1.025 and 0.591, we're going to use 0.591. Okay, so we will discard 1.025 that because that is greater than our initial concentration. So we're going to use 0.591. So we plug in 0.591 on x values here. So that means that will be 0.75 minus 0.591. Same thing here, 0.591. And then 2x, that will just be 2 times 0.591. Okay, so that means the equilibrium concentration for hydrogen gas is 0.159 molar for hydrogen gas at equilibrium. For iodine, that will also be the same, 0.159 molar at equilibrium. And for HI, that will be 1.182 molar at equilibrium. Okay, so that is the equilibrium concentration of our chemical species, no, using the ice calculation, the ice table calculations. Okay, so again, we started with initial concentrations only, then using quadratic equation, we were able to solve for the value of the concentration of each chemical species at equilibrium. Okay, so that's how we solve for it. Okay, so this is the usual step. you construct the ice table, you predict where the reaction is going, then whatever your E here is, you plug it into the K expression. After plugging in your concentrations in K, you solve for the value of X. Then after solving for the value of X, you go back to your ice table, you plug in the value of X, and then you get the equilibrium concentrations. Okay, so that's the steps. Okay, so again, you construct the ice table, determine where the reaction is going, whatever your E is, plug it into the K value or the K expression. After plugging in your E expressions here on your K, you solve for the value of X. And this is the lengthy process because it involves algebra. So you solve for the value of X, then once you were able to determine the value of X, you go back to your ice table, plug in the value of X, so you will get the equilibrium concentrations. Okay, so yeah. Okay, so this topic is purely ano lang, purely algebra, no? So yeah, yun lang. Okay, so last problem. Ay, this is a typo. This is on the lecture slides kasi. So wala yan. Wala na pala. Okay, so we only have two examples na. So again, I want you to practice on these two examples, especially with the calculator technique, no? Okay, so that uh, you will be ready with your quizzes, no? Also, I uploaded worksheets, no, where you can apply our lesson. Okay, so just go to your canvas. We're not yet done, no? Okay, so just go to your canvas and then look for the worksheet for part 2. Okay, this is the part 2 worksheet. Okay, so you can use these problems. Okay, so work on these 4 problems using the ice table. Okay, so you need to use the ice table uh, to answer the following problems, and then the solution are already posted, including the calculations. Okay, and the quadratic equations. Okay, so hopefully this will help you with your review. Okay, so if you have any questions, just message me. Okay, so there you go. You have the ice table, the K expression, the solving for the value of X. Then we go back to the ice table again to get the equilibrium concentrations. Okay, so I hope this worksheet will help you with the ice table calculations now. So I will leave that to you as your worksheet now. Okay, that will not be graded, of course. No? For the calculator technique has been uploaded on YouTube. I already commented the link here, so please check out if your calculator is capable of doing that. Okay, because if your calculator isn't able to solve for the quadratic equation, then you have to do it manually. Okay, the downside is that it will take you much longer time, okay, compared to just plugging in the values for ABC in your calculator. Okay, so please check out the video on that, on how to use calculator to solve for the value of X. Okay, so that will be our 2 problems with ice table. 4 other problems are posted on Canvas with solution. Okay, so let's proceed to the last part of our problem. So we have the factors that affect the chemical equilibrium. So imagine chemical equilibrium as a seesaw. Okay, so equilibrium is a seesaw. It is a balance between the reactants and the products. Okay, just a subtle change on the concentration of your reactants or the products, or by changing the state of the system, that can affect the balance. Okay, a small change in your system can affect the balance. Okay, so that means if you add few amounts of reactants, then the balance will be destroyed. Okay, if you change the state of your system, the balance can also be changed. Okay, so that concept was laid out to us by Le Chatelier in his Le Chatelier principle. So it states that if an external stress is applied to a system at equilibrium, then your system will adjust in such way that the stress is partially offset as the system reaches a new equilibrium position. So it means that when we when we alter the balance here, so if we change the balance, then the system will try to reestablish that. Okay. So the system will try to reestablish the balance if it is destroyed. Okay. So that means the reaction has to go either to the reactant or to the product side in order to reestablish the balance. Okay. Suppose I added too much product, then for this seesaw to be balanced out, then some of the products has to be converted back to the reactants. Okay. If I added too much reactants, then in order to maintain balance, some of the reactants has to be converted to the products. Okay. So that's the Ricciati principle. Whenever you uh, whenever you have external stress in your system, then it has to go to the left or to the right of the reaction in order to reestablish balance. Okay. So there are four changes that we have to take into account when it comes to Le Chatelier principle. Number one is the changes in concentration. So increasing the concentration of the products shift the equilibrium to the right. Okay. So that means if you increase the amounts of your products, then the reaction has to go to the left now instead of to the right now. I misread that. So if you increase the concentration of your products, then your equilibrium shifts to the left in order to reestablish the balance. Okay. If you decrease the concentration of your products, then the system will shift towards the right in order to reestablish the balance. Okay. So to help you memorize this, this is my analogy for the changes in concentration. So suppose you have two water buckets and they are connected at the bottom. Okay. So that means if they are connected at the bottom, their water level has to be equal when equilibrium is achieved. Okay. So the water level on those two buckets will be equal at equilibrium. Okay, so let's check this now. Let's apply this sentence into our logic. Okay, so according to this problem, if you increase the concentration of your products, okay, so that means I will add water on my right bucket. In order to maintain balance, some of the water on the right side has to go to the left side. Okay, so that means increasing the amounts on the products will shift the equilibrium to the left. Okay. So because you increase the water level on the right side, in order to achieve balance, some of the water has to go to the reactant side. Okay. Or some of the chemical species has to be converted to the reactant side. Next sentence, decreasing the concentration of the product shifts the equilibrium to the right. Okay. Suppose we have the same water bucket. Okay, so they have the same water line. If we decrease the amounts of the products, suppose we lowered down the amounts of our products, then that means the water on the left side has to go to the right side in order to achieve balance. Okay, so in chemical terms, your reactants will be converted to products in order to achieve balance. Okay, so use the water bucket analogy to determine whether the reaction will shift to the left or to the right when changing the concentration of your products or your reactants. Okay. So let's try reactants naman. The reactants point of view. Okay. So what will happen if we increase the amounts of the reactants? So increasing the water level on the left bucket will push the water to the right. So that means increasing the concentration of reactants will shift the equilibrium to the right side. Okay. Okay. If we decrease the amounts of the reactants, on the other hand, if we decrease the amount of the reactants, that means some of the water on the right side has to go to the left side in order to achieve balance. So that means the equilibrium will shift towards the left. Okay. So I hope the water bucket analogy will guide you to memorize the shift in the equilibrium when changing the concentration. Okay, so just imagine the concentration of your substances as the water in your buckets. Okay, so in order to achieve balance, your water can go to the left bucket or to the right bucket. Okay, so that pertains to the left side of the reaction and to the right side of the reaction. Okay, so that will be the first factor that affects the equilibrium, changes in concentration. Second one is the changes in pressure and volume. So according to this sentence here, if we increase the pressure, then it favors the reaction that decreases the total moles of gases. Okay. So that means if we increase the pressure of our system, then it will favor the side of the reaction with the lowest number of moles of gases. If we decrease the pressure, it will favor the side of the reaction that has the greater moles of gas. Okay, later on we will have some examples. Okay, so as of now, I don't have any analogy for this now. Okay. Okay, so just remember this, that when you increase the pressure, it will favor the side of the reaction with the lowest mole of gas. If you decrease the pressure, it will favor the side with the greater moles of gas. You just have to remember this. I don't have any analogies. Okay, so yeah. So for temperature, okay, so for temperature changes, if the temperature increases, it will favor endothermic reaction. And if the temperature decreases, it will favor an exothermic reaction. Okay. So what is an endothermic and an exothermic reaction? Okay. So endothermic reactions have delta H values that are positive. Okay. And exothermic reactions have delta H values being negative. Okay, so that means um, increase in temperature will be okay with endothermic reactions, so it will proceed to the right side, and a decrease of temperature is okay for exothermic reaction, so it will proceed to the right side. Now we can use the changes in concentration analogy for this one. Okay, so how? For endothermic reactions, imagine heat as a reactant. Okay. So again, for endothermic reaction, imagine heat as your reactant. Okay. So suppose you have A in equilibrium with B, and that is endothermic. Delta H is positive, then that means your heat is your reactant. If you increase the temperature, that means you are increasing the heat energy. Okay. So use the water bucket analysis analogy. So imagine heat as your concentration. Increase in temperature will mean increase in heat. Okay. So that means if you increase the heat for the reactant, the reaction will be pushed to the right. Okay. If that is an endothermic reaction. Okay. What will happen if you lower down the heat and the reaction is endothermic? Okay, so if you lower down the heat and the reaction is still endothermic, okay, take note we're still on the endothermic. If you lower down the temperature, that means you are decreasing the heat energy. So that will mean some of the products will be converted to the reactants. Okay. So again, for endothermic system, delta H is positive. Imagine that your heat is the reactant. So increasing the temperature, that means you will increase the heat. on the reactant side. So it will push the reaction to the product side. But decreasing the temperature or decreasing the heat will push the reaction to the left side. Okay? So that is for endothermic systems or for endothermic reactions. Your heat is on the reactant side. How about exothermic? Okay. So for exothermic reactions, imagine your heat as the product. Okay. So imagine your heat as the product. So that delta H value will be negative. Okay. So let's use our water bucket analogy. Okay. So if we increase the ay ba't di full screen? Teka lang. Hindi siya full screen. Wait lang. Hopefully, full screen na ta. Teka lang ha. Balik ulit tayo. Okay. Yun. Okay, so for exothermic reactions, imagine that your heat is the product. Okay, so that means A is an equilibrium with B plus heat. Okay, so that is exothermic reaction, or your delta H will have negative value. So imagine water bucket analogy again. Okay, so if you increase the temperature, that means your products will increase. Okay, will increase in amounts because you add heat. Okay, so when you increase the temperature, heat will be increased as well. So increase in temperature for exothermic reaction will push the water to the left. Okay, because again, when you increase the temperature, you increase the heat, so basically you increase the concentration of your products. Okay, so if that's the case, the reaction will proceed to the left. Okay, however, if you decrease the temperature, okay, so that means the heat is decreased as well. Okay, so decreasing the heat, that means you decrease the amounts of your product side. Okay, so decreasing the temperature will decrease the heat. That means the amounts of the products will decrease as well. So that will push the reaction to the right side. Okay. So you can use the water bucket analogy for the changes in temperature. Again, for endothermic reaction, heat is reactant. And for exothermic reaction, heat is a product. Okay. So, yan. And then lastly, effect of catalysis. Okay, so catalyst rather. So catalyst just lower the activation energy for your reaction to occur. Okay. So what is an activation energy? So activation energy is the energy barrier between the reactants and the products. Okay. Hopefully you can still recall your high school chem. So that is the barrier, the energy barrier between the reactant and the product side. Okay. What catalysts do is that they decrease that barrier so that the reaction will proceed smoothly. Okay. So when you add catalyst in your equilibrium system, it will not shift the equilibrium. Okay. It will change the speed of reaction. Okay. So it will change the speed of reaction, but it will not shift the equilibrium. Okay. Okay, so it will not change the equilibrium. It will speed up the reaction in both ways. Okay, so that means equilibrium is unaffected. Okay, so those are the four changes that Le Chatelier described in his principle. Changes in concentration, increasing products will shift the equilibrium to the left, decreasing products will shift the equilibrium to the right. Okay, so use the water bucket analogy for concentration changes. For pressure, increased pressure, that means it will favor the side of the reaction with less mole of gases. Decrease in pressure will favor the side of the reaction with more moles of gases. For temperature, use the water bucket analogy here. Okay, so for endothermic reaction, imagine heat as your reactant. And for exothermic reaction, imagine heat as your product. Okay, and the effect of catalyst, it doesn't shift the equilibrium. Okay, so let's try some examples here. So for this reaction, N2F2 in equilibrium with 2 moles of NF2, delta H is 38.5 kilojoules. Okay. What is the answer for the following questions? Okay, so let's try. Reacting mixture is heated to a constant volume. Okay, so when you say heated to a constant volume, that means temperature is increased. So what type of equation do we have here? What type of reaction do we have here? So since delta H here is positive, that means we have an endothermic reaction. So for endothermic reactions, imagine your heat as reactants. Okay? So since we increase the temperature, we are increasing the heat. So that means we are increasing the amounts of reactants. So in order to achieve equilibrium, the system will shift towards the right. Okay? It will shift to the right. Okay, because increasing the temperature will mean increased heat. So since we have greater amounts of reactants compared to products, it will push the reaction to the right side. Okay, so imagine the water bucket analogy here. So let's try that. Okay, so this is the water bucket analogy. Okay, so suppose we have um, two buckets with water at the same level. If we increase the temperature, if we increase the heat of the reactant side, that means we are adding water on the left side. And since we have more water on the left side than on the right side, it will push the water to the right side, or it will shift the equilibrium to the right. Okay, so that's the analogy here. Okay, so let's have letter B. Okay, some N2F2 gas is removed at constant temperature. So we remove some of the reactants. So imagine the water bucket again. So they are balanced, but if we remove N2F2, that means we are decreasing the water level on the left side. Okay. So since we have less water on the left side than on the right side, the equilibrium will shift to the left in order to achieve balance. Shift to the left. Okay, so the water level will shift to the left in order to achieve balance. Okay. So again, water bucket analogy will be helpful with the concentration and the temperature changes. Okay. So how about letter C? Pressure is decreased at constant temperature. So in terms of pressure, okay, so according to this slide, to the previous slide, no, increase in pressure will favor the side with the less moles of gases. Favors less mole of gas. Decrease in pressure will favor more moles of gas. Okay, so increase in pressure will favor the side of the reaction with less mole of gas. Decrease in pressure will favor the side of the reaction with more moles of gases. So just look at the stoichiometric coefficients of your gases. On the reactant side, I have 1 mole gas. On the product side, I have 2 moles gas. So if I decrease my pressure, I will favor the side of the reaction that has the more moles of gases. So in our example here, the side with the more moles of gases is the product side. So that means it will
favor the product side. So the equilibrium will shift to the right. Okay. So again, when you decrease the pressure, it will favor the side with the more moles of gases. Count the number of moles of gases in your equation. Then since on the right side we have more moles of gases here, then the equilibrium will shift towards the right. Okay. So what if you encountered a problem in which the moles of gases are equal? Okay. So suppose the moles of gas on the left side is 2, on the right side that's also 2. Okay. So if that's the case, no, that the number of moles of your reactants and the products are the same, then pressure will not affect the equilibrium system. Okay. So it will not shift the system to the left or to the right if the number of moles of your gas are the same. Only if they are different, then we can shift the system to the left or to the right. Now, depending on which side has the more moles of gases or the less mole of gases. Okay. Lastly, we have catalyst added. Then, according to the previous slide, no effect. Okay. So it doesn't shift the equilibrium in either directions. Okay. So again, catalysts, they will never change the equilibrium state. They will only speed up the reaction. So they speed up the forward and the reverse reaction by lowering the activation energy. Okay, so let's have another example. By the way, delta H is wrong here. Let me look for the correct value of delta H. Palang ha, hanapin ko lang. Let me look for the delta H value. That's a typo kasi. Okay, so that will be positive 284. Okay, so we still have an endothermic reaction. Okay, so again, if we have an endothermic reaction, imagine your heat as the reactant. Okay, so let's answer the following. Okay, first one, increasing the pressure of the system. So since we are talking about pressure, check first which side of the reaction has the greater moles of gases. On the left side, we have 3 moles of gases. On the right side, we have 2 moles of gases. So as I told you earlier, increase in pressure will favor the side with the greater, less moles pala. That will favor the side with the less mole of gas. Decreasing the pressure will favor the side of the reaction with greater mole of gas. So since we increase the pressure here, we will favor the side of the reaction which has less mole of gases. In our case, the right side. Okay, so that means the equilibrium will shift towards the right side. Okay, shift to the right. So that means the products will be produced in order to achieve the equilibrium. Okay, so adding oxygen to the system. So use the water bucket analogy here. So if I add oxygen in the system, then that means I add water on my left bucket. Okay? Because on the reactant side, I have my oxygen gas here. So adding oxygen will add water to my left bucket. So in order to achieve balance, it will push the water to the right, or the equilibrium will shift to the right. So it will produce products in order to achieve balance. Okay. How about letter C, decreasing the temperature? Okay, so decreasing the temperature. So that means if you decrease the temperature, you reduce heat. Okay, so by lowering the amounts of the reactant, that means the equilibrium will shift to the left. Okay, so by decreasing the temperature, we decrease the amounts of the reactant. So our equilibrium will shift to the left, to balance them out. Okay. So you can still use the water bucket analogy for the temperature changes. Shift to the left. And then lastly, adding a catalyst, no effect. Okay. So again, when we talk about pressure, we will favor the side of the reaction with the greater moles of gases if pressure is decreased. If pressure is increased, we will favor the side of the reaction with less moles of gases. Okay? For for adding or for changing the concentration of your chemical species, then you will favor the side of the reaction that has the lesser amount. No? Okay, so imagine the water bucket analogy here. Same as for temperature. For endothermic reaction, imagine heat as your reactant. For exothermic reactions, imagine heat as your product. Okay. Using the same analogy, the water bucket analogy, you can predict where the reaction is going. Okay. So increasing the temperature increases the heat. Decreasing the temperature decreases the heat energy. Then lastly, catalyst doesn't affect the equilibrium system as it only speeds up the rate of reaction. Okay? So it speeds up the reaction, but it will not shift the equilibrium system. Okay? Okay, so last one, we have the common ion effect. This will be discussed further in your laboratory chapter 4 discussion. Okay, so what's common ion effect? So common ion effect is an application of the Le Chatelier principle. Okay, so it states that a salt will be less soluble if one of its constituents are already present in the solution. Okay, so suppose we have a salt, let's say KCl. So potassium chloride will dissociate into potassium ion and chloride and ions, di ba? Suppose your system already has chloride ions from NaCl, okay? So suppose we add NaCl. So that means the concentration of Cl will increase. So since the amounts of our products is greater than the reactants, then the equilibrium will be shifted to the left. That means KCl will be less soluble, okay? Because according to Le Chatelier principle, if you have increased amounts in the product side, it will push the system to the left side, okay? Uh, so that means the salt will be less soluble if you have common ions. Okay. So this will be discussed in depth in your laboratory now. Okay. I'll give you some more examples pa. So suppose we have barium sulfate. So for barium sulfate, this will dissociate into barium 2 plus and sulfate ions. Suppose your system or your equilibrium already has barium ions from, let's say, barium chloride. Suppose you already have barium ions, okay, in your system before you add the barium sulfate. So since we have more products than the reactant, it will shift the reaction to the left side. So that means barium sulfate will be less soluble. Again, this is only true if you have common ions. Okay, so it could either be the barium 2 plus or the sulfate ion. Okay. However, if you have uncommon ions, okay, so suppose you have NaCl, okay, so this will dissociate into this one, okay, and then suppose I add, let's say, silver nitrate, okay, so that will be silver ion and nitrate ions. Suppose I add silver nitrate in my NaCl solution. What will be the effect? Okay. So the effect when you add ions that are different with your salt, okay, will be discussed next chapter. So this phenomena is called the diverse ion effect. Okay. So we will see more of this next meeting. Okay, next week. We will discuss the diverse ion effect. Okay, what is the counterpart of the common ion effect is the diverse ion effect. Okay, so it will also change the equilibrium, but in a different way. Okay, so that means by next meeting on chapter 4 discussion, that will be the last chapter before the midterms, we will still use algebra. Okay. Okay, so yan, because we will be talking about equilibrium again with diverse ions. Okay, so yan, so that will be all for chapter 3. Okay, so again, to summarize everything for chapter 3, let's recall. So to summarize everything for chapter 3, we were able to discuss the equilibrium concept. It states that the equilibrium is a state of system in which the forward and the reverse reaction are equal. We describe equilibrium systems with the equilibrium constant. So it tells us the ratio of the amounts of products and the reactants at equilibrium. Okay. In writing the K, we have two ways to do that. We have the Kc and the Kp. Kc is when your products and the reactants are expressed in molar concentration. Kp is when your products or your reactants are expressed in pressure units. Okay. So also we do not write the solids and the liquids and the equilibrium constant. That will also be discussed next chapter. Okay. Uh, yeah, so we only write aqueous and gaseous phases on the equilibrium constant. If you have aqueous phases, then you can only write Kc. If you have gaseous phases, you can write both Kc and Kp. Okay. So depending on how you balance the equation, you can have different k values. So if you shift, I mean in the shift, if you flip, if you flip the equation, that means the k value will be reciprocated. If you divide the equation by 2, then the k value will be uh, the square root of it. Okay. And if you multiply the equation by 2, then the k value will be squared, so on and so forth. And then when you combine equilibrium constants, you multiply the k values. Okay. We can use the reaction quotient to predict the direction of reaction. So reaction quotient has the similar expression as K. However, the initial concentrations are to be written. So depending on your K value, you can tell whether the reaction is going to the right side or to the left side. Just use the number line analogy we had last time. Okay. So suppose you are given the initial amounts, then you are asked to solve for the equilibrium concentration, then you can use the ice table. So what is an ice table? It is a table in which we can track the changes in the concentration of our chemical species. Okay. So I stands for the initial amounts, which will be stated on the problem. If the species isn't stated, then that means the initial concentration is 0. Okay, so again, if it is not stated, it is automatically 0 in initial concentration. The C stand for the changes. So the change could either be positive or negative depending on the direction of the reaction. You can use the Q reaction quotient to determine the direction of the reaction, or you can use Le Chatelier principle to predict where the reaction is going. Okay. So if the reaction is going to the product side, then the change for reactant is negative and the change for product is positive. If the reaction is going to the left side, then the change for the reactant is positive and the change for the product is negative. Okay. Also, you must include no, you must include the coefficients in your change. No, suppose your species has this coefficient equal to 2, then your change will be 2x. Okay, if you have a coefficient equal to 3, then the change will be 3x. Okay, if that's 4, then that's 4x. Okay, if you have 1/2 coefficient, then that means the change is 1/2 x. Okay, so yun. What else now? E is the equilibrium now. So what you're going to do is just add the I and the C to get the E. Okay, so you add I and the C to get the E. Whatever the E value is, you're going to plug it into the K. Then you solve for X algebraically. Okay, you may do quadratic equation or trinomial equations now, but in the end you will get x values. Okay, so if you have multiple x values, we have two criteria in selecting which among them will be used for the equilibrium calculation. Number one, the x must be positive. Okay, so x must never be negative. Okay, so we only choose the positive value for x. Second one, if they are both x, if both x values are positive, then you choose the x that is less than the initial concentration. Okay, because if your x value exceeds the initial concentration, then most likely you will get a negative concentration at equilibrium for that species, and that's wrong. Okay, we do not have any negative concentrations. So take note of that when solving for equilibrium problems. Okay, so yan. So yan, after choosing the x value, you plug it again into your ice table to get the equilibrium concentrations. Okay. Then lastly, Le Chatelier principle. So it tells us that the equilibrium will shift in order to reestablish it, no, when the system is stressed, no, or when the system is changed. So there are four subtopics for the Chatelier principle: changes in concentration, changes in pressure, changes in temperature, and catalyst. No? Among those four, catalyst will not shift the equilibrium. Okay. Also, we discussed this briefly, the common ion effect. It tells us that whenever we have common ions with our salt, then it will shift the equilibrium to the left so that the salt will be less soluble. Okay, so more of this will be discussed on chapter 4 laboratory, which will discuss acid-base equilibrium and solubility equilibrium. Okay, so what if we add diverse ions? Okay, so when you say diverse ions, these are ions different than your salt. No? For example, you have NaCl. If I add silver nitrate, that's diverse ion. No? So what will be the effect of diverse ion with your salt? We will discuss that next meeting, okay, for the next chapter, for the last chapter before the midterms. No? Okay. So our schedule, no? So before we end our session, our schedule will be this one. So on Friday, March 5, March na pala. So March 5, we will discuss chapter 4. If we will not be able to finish that, we will use March 12, no? But hopefully, I'm still hoping that we can finish everything on March 5 so that by March 12 we can start our review sessions na. No? I will upload more uh, worksheets no on the week before the exams. Okay. So hopefully those worksheets will be useful for you when you review for your quizzes and the midterm exam. Midterm exam will start by March 15 until March 20. Okay, so this is the anniversary of our lockdown here in the Philippines. No? So 1 year na nakalipas. So again, the worksheets are uploaded in your Canvas. Just go to announcements, go to additional resource materials, and then you have your worksheets here. Okay, so if you want to take a look at the laboratory worksheets, then feel free to use them. Okay, so use these worksheets here. For students, no, for Filipino students who want to watch the Taglish version of my discussion, no, Okay, so you may want to check the recordings for sections 1 and section 14. Okay, so if you want Taglish discussions, rewatch section 1 and section 14 discussion. Okay, if you want to watch my lab classes, okay, so you just look for the videos with title section 2, 6, and 15 on our YouTube playlist. Okay, so also I update this post every now and then. Okay, so whenever I have new worksheets, I upload it and um, update this post here. Okay, so I will inform you naman when I update this file, this post. Okay, so that will be all for our discussion today. Um, hopefully you will get high scores on quizzes part 1 and part 2 for chapter 3. Okay, so again, part 1 is open starting from now until Monday. 60 minutes, only one attempt will be given. For part 2, that will open starting March 3 until March 6. You will have two attempts, 45 minutes per attempt. Okay, so that will be all for today. Good luck with your review. If you have questions regarding our classes, please don't hesitate to message me here on MS Team. So I will reply to you as soon as possible. Okay. So again, if you have any questions, just message me na lang. Okay. So I'll see you again next week. So good luck with your quizzes. Okay. So a copy of the video will be uploaded on YouTube. Okay. So that will be all.